We are saying a mole is the amount of substance that contains as many entities as they are in exactly 12 grams of carbon 12 isotope. Right? So any amount, it doesn't, when you're talking about amount, meaning that some amounts can be very big but it contains a mole. Others can be very small but they all contain a mole. So by looking at the quantity of something, you are not going to be able to determine how many moles it has. Okay, so whether you have got, let's say, 1 mole of carbon dioxide or 1 mole of, let's say, copper, they are all going to contain the same, what, I'm not they are going to contain the same particles. They are going to contain the same particles even if they are different things or compounds. Why? Because they are all 1 mole. So basically, when you are talking about 1 mole of something, 1 mole of anything is going to be equal to the Avogadro's number, meaning that is going to be 6.022 multiplied by 10 to the power 23. It can be particles. So 1 mole of something can be Avogadro's number of particles, or 1 mole of something can be Avogadro's number of atoms. 1 mole of something can also be Avogadro's number of molecules. 1 mole of something can also be Avogadro's number of ions. So 1 mole of something is 6.022 times 10 to the power 23 atoms, molecules, ions, or whatsoever. So if they say you've been given 2 moles of sodium chloride, okay, you've been given 2 moles of sodium chloride, and then they ask you to find the number of ions of sodium present in 2 moles of sodium chloride. How do you get to find that? So what you are going to do is, since you want to find the number of ions of sodium in sodium chloride, you get this sodium chloride. This can break. Okay, the sodium is able to break the sodium chloride, that is going to form sodium ion and the chloride ion. Okay, so you can see that when you have got one sodium chloride, you are going to have one sodium ion and one chlorine ion. What does this mean? This means that one sodium chloride is equal to one sodium ion. And actually, this is just 1 mole. 1 mole of sodium chloride is equal to 1 mole of sodium ion, which is equal to 1 mole of chloride ion. Now, today I don't know what's up with your network. I don't know your place today. So if you want to find the number of sodium ions present in 2 moles of sodium chloride, since you can see that the number of sodium ions is equal to the number of full sodium chloride, that means that if you have got 2 moles of sodium chloride, then you also have what? 2 moles of sodium ion. So to find the number of moles of sodium, to find the number of ions of sodium, you know that 1 mole of sodium ion is going to be equal to 6.022 times 10 to the power 23 ions. Okay, now you have got 2 moles of sodium ion. How many number of ions are you going to have? X. So simply cross multiply. If you find this value of x, then you'd have determined the number of ions which are present in what? In 2 moles of sodium ion. So that is how you're able to find. So if you are given this as mass, yes, Fabi.
Sir, I have a question. There where on the main question you said we are finding the number of 2 moles of sodium ion.
Find the number of ions in 2 moles. Find the number of sodium ions in 2 moles of sodium chloride.
Okay, thank you.
Okay. So now what if this was not 2 moles of sodium chloride, but it was 2 grams of sodium chloride? We are going to use the same formula, but first thing we need to find the number of moles of sodium chloride. How do you find number of moles? Is given by mass over molar mass. Right, so you are going to say the mass, which is 2 grams. The molar mass, you check on the periodic table. Sodium is 23, chlorine is 35.5. So when you add that, that will be the molar mass you are going to be able to use. So let me just try to do that. So we are saying sodium is 23 plus 35.5. So this is going to give us 58.5 grams per mole. That's the value you find on the periodic table. So if you divide 2 over the value, so that is going to give you 0.034. Now I may just try to log out and then log in. It's going to start showing. So these are going to be the moles of sodium chloride when you have been given 2 grams of sodium chloride. Now you know that a mole of sodium chloride is equal to a mole of sodium, right? Meaning that these are also the same moles of what? Sodium chloride. So basically, if they say find the number of sodium ions in 2 grams of sodium chloride, then you are going to say 1 mole of sodium ion is equal to 6.02 times 10 to the power 23 ions. What of now these moles which you have found of sodium ion, how many ions are they going to give us? So that is how you are going to be able to calculate. So just to mention that now, the last one on that. Let's say you've been given, uh, can we say calcium chloride? Let's say we've been given 4 grams of calcium chloride. And then the question is find how many ions of chlorine are there, or how many chlorides ions are there. Are there in what? Are there in 4 grams of calcium chloride. Okay. So also for this question, you first need to find the molar mass for calcium chloride. Now, how do you get the molar mass for calcium chloride? You just go on the periodic table. Calcium chloride. Now, chlorine, we said the molar mass on the periodic table is about 35.5. Multiply this by a 2, alright, because you have got 2 chlorines. And then you have got calcium. Calcium is just 1. Multiply by the molar mass of calcium, that is 40 on the periodic table. I don't have one, I might error, so you can check if you have. So that 5.5 multiplied by 2, that gives us what? 71. 71 plus 40, that is going to give us 111 grams per mole. So I'm going to determine now the number of moles of calcium chloride. Number of moles is given by, what's the formula for number of moles? Feb, what's the formula?
Mass over molar mass.
So that would be mass divided by molar mass. And the mass, we have got 4 grams. The molar mass, we have got 111 grams per mole. Right, so this is going to be 4 over 111. And that is going to give us 0.036 moles. Now, if you look at calcium chloride itself, when this one disassociates, you are going to have calcium ion, and calcium is in group 2, meaning that it forms a charge of positive 2 because it's a metal, right? It's going to lose 2 electrons. Chlorine is in group 7, meaning that it gains 1 electron. Okay, like that. Now, here you have got 2 chlorines, meaning that I have to balance by putting a 2 here. So 2 chlorine ions are going to react with 1 calcium ion to form calcium chloride. This is telling you that 1 mole of calcium chloride is actually going to form 2 moles of chlorine ion. Okay, So now, what of if you have got, look at the moles of calcium chloride that we've calculated. What of if you have got those moles? So 0.036 moles of calcium chloride. How many chlorine ions are you going to have? So number of moles of chloride ions, right? So this is going to be number of moles of chloride ions will simply be 2 multiplied by 0.036, and that is going to give us 0.072 moles of chloride ion. Okay, now remember, we want to find how many ions. How many ions? You know that one mole of anything is equal to 6.022 times 10 to the power 23, either particles, ions, molecules, or atoms. Now here we are talking about ions. What of 0.072 moles? How many ions are they going to give us? X. So X will just be 0.072 multiplied by 6.022 multiplied by 10 to the power 23, and that is going to give us 4.34 multiplied by 10 to the power 22 ions. So these are the number of ions. Yes, Nathan.
Yeah, so I'm kind of asking to where there is the one more calcium chloride is equals to two more chloride ion. So I'm not clear on that part.
Oh, okay, okay. So if you see calcium chloride itself, since calcium chloride contains one calcium and two chlorine atoms, when it disassociates, it's going to give you one calcium ion and then two chlorine ions, meaning that one mole of calcium chloride upon disassociating is going to give you two moles of chloride ions. That is why we are saying one mole of calcium chloride is equal to two moles of chloride ions. It's coming from the disassociation equation that we're able to see. Is it okay?
Yes, I'm clear now.
Okay. Do you have any other question? Any other question?
Yes,
Yes.
yes, I have a question. I don't know how you found. I'm not clear on the part where you found 0.072.
Just divide mass by molar mass. That will give you 0.07, 0.036. And then you come down here. You know that one mole of calcium chloride is 2 moles of chloride ions. Now you have got, from what you've calculated, the number of moles of chloride ions, they are 0.036. How about the number of moles of chlorine? Those are the ones we're going to find.
Or it's a continuation from down there, you cross multiplied and everything. That's how you found the 0.072.
Yes.
Okay.
Alright. So this was an introduction so that you understand something about moles. Now, we have got something which is called the relative atomic mass. Relative atomic mass. Now, when you are talking about the relative atomic mass, the symbol we give is A with RS there. Relative atomic mass is just the average mass of an atom. Like the average mass of an atom. That's what we call relative atomic mass. The average mass of an atom. Now, why are we saying average mass of an atom? Okay. So the average mass of an atom, of an element, relative. So when you're comparing it like to carbon 12, Now to make it simple, let me just say average mass of an atom. Right. So a simple definition we can give of relative atomic mass, if you want a definition, because I'm not interested in the definition. Relative atomic mass of an element is the average mass, okay, in grams of the number of atoms of the elements contained in 12 grams of carbon 12. Like, if you're talking about relative atomic mass of an element, how much mass is in 12 grams of carbon 12 for any element? That is what you call relative atomic mass. For example, if an atom can go into carbon 12 15 times, that's the relative atomic mass. So relative atomic mass is just the average mass of the number of atoms of an element which is contained in 12 grams of carbon 12. That's a simple definition. Now, we are bringing in the word. Remember, when you have got an element, let's say I've got an element here, x, you have got a number here, and then you have got a number here. Who can tell us what z is representing? What is z representing here? Yes, Titus.
Mass number.
And then a is representing what?
No, Z is presenting total number, then A mass number.
Okay, so this is the number of protons, or the atomic number, and then this is the mass number. Okay, so at some other elements you'll see they've swapped these, but what I want you to know is that, let's say you have got 6 here, here you have got 12. This is the mass number, right? That's the mass number. Now for the same element, all right, you can have the element, let's say you have got the element x. It can have different atoms. All right, the same element can have different atoms. You are going to find they all have the proton number of 3, but this one has got a mass of 6, this one has got a mass of 7. All right, this is what gives us the isotopes. Isotopes are atoms of the same element with the same proton number but different mass numbers. Now, because you have got different mass numbers for the same element, that value that you see on the periodic table, they will get the average of this one. All right, and then because if I just say, okay, the mass of the relative, I get the mass of x, I put on the periodic table as just 6. What of this one? Because it is also x, right? So that is why they get to find the average. In it, let's say you've been writing test, you wrote test 1, you wrote test 2, you wrote test 3. They want to see how much overall you've performed in the term or in the semester. They will not just say, okay, let's get his test 1 because he had a 0%, so he got 0 the whole semester. What of if this one you got 70, this one you got 100? So that's why there is something called average. You find the average of these, right? So that is what we call relative atomic mass. So relative atomic mass is different from mass number. Mass number is just the number of protons plus neutrons. Now relative atomic mass is the average mass of an element. So mostly the periodic table that was used in high school, you find that the value they've used was the mass number. Just gotten something from one of these or rounded off. Now here you are going to be using a periodic table that is going to have decimals for the masses. That's relative atomic mass. That's the only way you can have a decimal. For example, you are going to see that for oxygen, the relative atomic mass is 15.9994. In high school, we used to use 16. They just rounded off this. For mass number, mass is just counting how many protons plus how many neutrons. You can't have a decimal for counting. Like after counting people in Zambia, you say, I found that in Zambia we have got 2.561 people. How possible is that? What do you mean by 2.561? So you can't have a decimal when you are counting. Okay, when you are counting, you can't have a decimal. A decimal point just comes in when you are measuring. So when you are calculating the relative atomic mass, since you are saying it's the average mass, you are going to find that this element X, since you have said that it has got different forms, you are going to find that the first form, of course, they are all having a mass of 3, right? This one has got, I mean, a proton number of 3. This one can have a mass of 6. This one has a mass of 7. Now you find that every time you get a sample, like you have not planned it, you just get a sample of X, you are going to find that when you get that sample, 70% of the sample you have gotten will always be that one with a mass of 6. And then the other percentage which is remaining, what percentage is remaining, Martha? Okay, 30, because the percentages should always give 100. So the other 30% which is remaining should be what? Should be the other one which has remained. So these percentages is what we call percentage abundance. Percentage abundance, how much of something is there. So to find the relative atomic mass, which we can also say A with the R, is given by the first mass multiplied by its abundance plus the second mass multiplied by its abundance. If you have got another one, plus that mass with its abundance plus, it continues to go like that. It doesn't matter how many there are. Now in this case, since we only have two, so we're going to say the mass. So this one has got a mass of 6. Now again, now don't take this one as a mass always. For me, I've said this is the mass. Okay, because sometimes they're going to give you like this and then they say its mass is, let's say, 6.01, so you take the one they've given you. Now for me, I've said the same number you are able to see here, that's the mass we're going to use, or that's the relative atomic mass for that element, just this atom. Now we are finding the average mass, so you are going to get that mass multiplied by the abundance. Now you don't multiply by a percentage, you don't want to find the answer in percentage, multiply. What is 70% as a decimal? Anyone please to help? How can you convert 70% into a decimal? Titus? Abigail?
0.7.
Okay, 0.7. So you just say 70 out of 100. And then plus mass 2, that is 7, multiplied by the abundance, 30 out of 100. Okay, let's say if we had another x there which had the mass of 8. So meaning that this wouldn't be 70, this wouldn't be 60. Perhaps maybe the first one would be 60. Okay, meaning that this one is going to be 10%. So also add plus 8 multiplied by 10 out of 100. And then you just punch this, friends. You just punch this. Say 6 multiplied by 0.7 plus 7 multiplied by 0.3 plus 8 multiplied by 0.1. The answer you get is the answer that is going to be the relative atomic mass of that element. That's the average mass after you consider all the atoms that element has. If you consider hydrogen itself, hydrogen has got 3 versions. You have got hydrogen 1, you have got hydrogen 2, you have got hydrogen 3. Okay, these are isotopes. So the mass you're going to see on the periodic table, 1.008, this is the average mass. It is not a mass number. That's the average mass or relative atomic mass. Do you have questions?
Kindly repeat on percentage abundance.
Percentage abundance is simply how much, like the composition of something. How much. So if I get a sample, for example, if you get a sample like from a class, okay, let's say from your class, you just get any random 10 people. You find that from those, let's say 6 have got brown eyes, whilst 4 have got blue eyes. So this is the abundance. Now if you express it as a percentage, 6 out of 10 times 100, that will be a percentage. So just if you get something randomly, how much more are you able to find this particular portion or this particular character? That is abundance. Is that okay? All right, let's answer these two questions. Two stable isotopes. There's a question before we answer, Nathan, or I can proceed with the question.
Yeah, the way we were dividing 100, you multiply. What if you add all those abundances multiplied by masses, then the overall
You divide
divide
by
by
100.
100? Can it give a wrong answer, or you're supposed to write the way you did?
It will give you the same answer.
Thank you.
Yeah, but I would advise you just take it like that. It is much simple. Like it's much simple taking it like that. Okay, two stable isotopes of lithium, six. So of lithium, you have got six lithium and seven lithium. You've got respective abundances of 7.5% and 92.5%. Six lithium, they've said, has got a mass of 6.05. This is what the lithium with 6. Okay, and then the relative atomic mass is 6.94. This is the relative atomic mass. Now the question is find or calculate the mass of lithium 7. So what is the mass of this one? We don't know. Now if you consider the abundances, 7.5% and 92.5. So they've said the first one to be mentioned is 6 lithium, and there is the word respective, meaning that the first one mentioned with the first abundance mentioned. So this 6 lithium has got an abundance of 7.5. Okay, the abundance is 7.5%, and then the other one, which is 7 lithium, the abundance is 92.5%. Now the question is want to calculate M, which is missing. So we'll say relative atomic mass is given by mass 1 multiplied by abundance 1 plus mass 2 multiplied by abundance 2, since we only have 2. The relative atomic mass has been given, that is 6.941. That is going to be equal to mass 1, that is 6.015. Multiplied by the abundance has been given here, 7.5. So I'll say 7.5 over 100. Okay, and then plus mass 2. Now mass 2 is not given, that's actually what we want to calculate, right? So I'll say mass 2 and then multiplied by the abundance has been given as 92.5%, so we'll say over 100. Okay, so this is going to give us 6.941, and that is going to be equal to, let's get to divide. I'll start first by saying 7.5 divided by 100. The answer I get, and now multiply by 6.015. That is going to give us 0.451125. And then plus, I'll say 92.5 divided by 100. That is going to be 0.925. And then multiply by m2. So take this term, you take it the other side, right? This is, I think, arithmetics we've known. So it will become negative, right? So we are going to have 6.941 minus 0.451125, and that is going to give us 6.489875, and that is going to be equal to 0.925 m2. So to remain with m2, divide both sides by 0.925, and that is going to give us 7.016, right? This is going to be the relative, that is going to be the mass of 7 lithium. 7 lithium, this is the value. Do you have any questions? Is this okay? Gracious, are we together? Fabi, yes, please go on.
So you're too quick. Can you slow down a bit?
I'm too quick.
So it's like you're doing everything fast, and then we are copying. So
You don't need to copy when I'm. You copy the tutorial is there for you. All right, let's look at this one. two stable isotopes of lithium, 6 lithium and 7 lithium, have got masses actually of 6.015 and 7.010 respectively. If the relative atomic mass of lithium is 6.941, calculate the abundance of each. Calculate the abundance of each. Now, I'm going to get, we have got 6 lithium, we have got 7 lithium. Let me write here 6 lithium. We also have 7 lithium. And then you've been told their masses. So the first one which was mentioned is 6 lithium and its mass is 6.015. I'm trying to slow down. 6.015. And then we have got 7 lithium. Feb, what's its mass?
7.010.
7.010. And then what's the relative atomic mass of lithium? Yes? Yes, Emmanuel.
Yes, right. 6.941.
Very good. 6.941. Okay. Now, our question is to calculate the abundances of these two isotopes. Now, you know that when you have got two isotopes, when you add their abundances, what should you get? 100.
100.
And the 100% as a decimal. 100% as a decimal is equal to what? It is equal to 1, right? Because 100% is 100 over 100. Very good. Meaning that if the abundance of this one is x, then the abundance of this other one is going to be 1 minus x. Now, this x is representing abundance as a decimal. Okay? So if I say the abundance of this one is y, then the abundance of this one is going to be 1 minus y. It doesn't matter. You choose which one to take. It's your choice. It's your choice. As long as at the end you're going to state it. So I'm using decimals, alright? I'm using decimals. So we're going to now say relative atomic mass is given by mass 1 multiplied by abundance 1 plus mass 2 multiplied by abundance 2. So the relative atomic mass is 6.941. And that is going to be equal to mass 1. Mass 1 has been given there 6.015. And then its abundance, we've seen that is x. And then plus mass 2, which is 7.010. Its abundance, we've seen that is 1 minus x. So just do the multiplication. Your aim is to find the value of x. 6.941 is going to be 6.015x. And then multiply 7.01 multiplied by 1, that would be 7.010. 7.01 multiplied by x, that will be 7.01x. Yes, Fabi, you have a question?
So I didn't understand there where did you get the 1 minus 8 and the x?
You can use anything. If you want to use f, your name, Fabi, and then here to be 1 minus Fabi. So the thing is, when you have got, let's say you have got two things that are supposed to add up to 100, and then one is giving you 40%. What will be the percentage of the other one?
60.
How did you find 60? How did you find the 60?
40 plus x is equals to 100. Then x, then 60 goes, 100 goes that side, then 100 minus 40 is equals
Okay, so what you did is 100 minus 40, right? So now, if you know, now let's say 40 is x. Okay, so this is x. And then you want to find this 60. It means it is going to be 100, where there is 40 to be what? X. Alright, but 100 as a percentage, as a decimal, is 1. So that's why we're saying 1 minus x.
Okay, thank you.
Okay. So now we'll just get to take like terms to the same side. So this is going to be 6.941, and then I'll take the 7 on the other side, so it's going to be negative 7.01, and that is going to be equal to 6.015x minus 7.01x. So let's subtract now. We have got 6.941 minus 7.01. This is given me negative 0.069, and that is going to be equal to the other side. We also say 6.015 minus 7.01. This is going to give you negative 0.995x. Now divide both sides by the negative 0.995 so that you remain with x. So x is going to give you, let's divide negative 0.069 divided by negative 0.995. This is given me 0.069346733. Remember, this is a decimal. Remember what was x representing? Now this is where we need to take note. If you said x represents 7 lithium, don't confuse them. So we have found now that the value for x is 0.0693. I can just write them to 3, meaning that what will be here. So just say 1 minus 0. Where there's x, we put 0.0693, meaning that this one is going to be 1 minus, that is going to give us 0.9306. Okay, these are decimals. So meaning that the percentage abundance for 6 lithium, if you want to convert a decimal to percentage, just multiply by 100. So times 100%, since we want to convert percent. Since when you have got a percentage, you divide by 100 to go to a decimal. So if you have a decimal to go to percentage, just multiply by 100. So the decimal point goes 1, 2. So that is going to be 6.93%. That's the abundance for 6 lithium. And then 7 lithium, the abundance, also multiply this one by 100%. So that is going to be 93.06%. So these are the percentage abundances of the two isotopes.